Ladies and gentlemen, my first slide is actually not about the topic of this talk. It is this one. And I wanted to realize that Yuri was among the first. Maybe he was the first. I'm not so sure, and I don't want to do injustice. I don't want to be unjust to people like Giovini, Carlyle, maybe a few others, Karatsas. He was among the first who proved a true set-valued duality theorem. And this theorem is from his oops, where is the, oh, this one. How can I move this green pointer? Sorry, can you help me for a second?
No idea. You want to point?
Yes, I want to point.
This one. The point is it?
It's not working.
It's not working.
It's not working.
Yeah. Okay. Okay, but I can continue with this slide, okay? So Yuri was among the first one who proved the true set-valued duality theorem, and when I realized that this theorem actually is a consequence of a very general convex duality theorem, namely the Fenchel-Moreau biconjugation theorem for set-valued functions, I was very happy. Because I thought from now on, I don't have to justify myself why I do set optimization and why I do it the way I'm doing it. Because there is a very nice particular case. Can I get this particular case back, please? Which is a super... This, okay, which is a super hedging theorem due to Yuri. So, and it roughly says that there is a set gamma which equals another set called D. And those two sets are the values of a coherent set-valued, convex, proper, closed risk measure. So this is the theorem. However, it turned out that I still had to justify myself. I mean, I realized this like roughly 10 years ago, and it was not that everybody was convinced. This convinced quite a few people, some of them even in this room, but not too many, let's say. So that's why I tried to move on, okay? So I moved on to very simple questions like this. Sometimes I think that we as mathematicians try to solve very complex problems because we cannot answer the simple questions. So here is a simple question, and I think that basically everybody here in this room has done something like a course, probability 101 or statistics 101, something like that. So do you have an answer to this question? When I started the work on the topic, I thought, yeah, there must be some kind of textbook answer. And I started searching in the literature, and the answer is no, there isn't. In fact, there is a huge, let's say, discussion in the statistical literature of how to define the median, or more general, the quantile of a multivariate random variable. So I will do without this. So just to recall a few things, here's the definition of the cumulative distribution function for a random variable. This is the lower p quantile. It's an infimum over some set. This is the upper p quantile, and the upper and the lower p quantile are kind of inverses to the cumulative distribution function. And the question now is, what happens if d is strictly greater than 1? In 2 dimensions, 3 dimensions, and so on. What's the problem with this definition? Well, the definition of the CDF, of course, depends on the order in the real numbers. And the infimum is very hard to generalize from dimension 1 to dimension greater than 1. So the question would be, what is this expression here involving the infimum in some d-dimensional space? So this is the question, and we could, for example, think of replacing the usual order in the real numbers by a vector order which is generated by a closed convex cone in Rd. So it turns out that some people had this kind of idea, and they, for example, used for the case that the cone is just RD plus the joint distribution function. Okay, so they wrote this expression, however, it didn't work. Even worse, some statisticians say that this doesn't mean much. So that means it is not very useful for statistical analysis if you do it like this. And instead, the statistician came up with concepts like so-called depth functions. And those depth functions basically replace the cumulative distribution function in the univariate case for statistical analysis, right? So, and here is, now I would really like to have my green pointer. Here is a picture that explains the difficulty with the infimum. So you see, consider this set capital A, and now the order generated by the cone R2 plus. And where is the infimum of this set A? So this is a red dot on the lower left. And you can see the infimum does not belong to the set. And the same applies to the supremum. And that's exactly the problem. And it's even worse because, I mean, R2 plus is a very nice cone. It generates a vector lattice. So there is an infimum. But some cones, for example, do not generate lattices, so you don't even have infima for 2 points, not to speak of bigger sets. And even in R2, there are certain sets which do not have an infimum. So there's lots of trouble with the infimum. So the remaining question, or let's say the question put a little more precise, is what is the quantile of a multivariate random variable in the presence of an order relation for its values? That's my question. Here are some quotes from the recent statistical literature. Let me mention that the paper by Belloni and Winkler in the Annals of Statistics is one of the very few papers who took this question seriously and tried to give answers depending on the order for the values of the random variable. But the approach in this paper is very, very different than my approach. Somebody changed the slides. And here is another quote by Mark Hallen, very recent. So you see, this is green now. Thank you very much. I'm happy. Okay, this is a quote very recent by Mark Hallen, with whom I also discussed this kind of stuff. And you know, the statisticians, they always complain that there is no canonical order in higher dimensions. Okay, so my answer to this is, if you're missing something and you have some trouble with something, instead of finding bad substitutes just embrace the situation and make the best out of it. And this is what we tried to do together with Daniel Kostner, my PhD student. And just an observation, which is very useful for the higher dimension case, you can write the set of lower quantiles like this, and then they're directed upward in the sense that if you add any positive number, you stay in the set. And the quantile, the lower quantile, is just an infimum over this set. And in the same way, oops, no. The upper quantile is directed upward, this set of upper quantiles, and the upper quantile is the supremum of this set. So yeah, it's directed downward. So, and you know that in the univariate case, lower quantiles are sufficient. So that means any upper quantile can be computed by means of some lower quantile. So you don't need to discuss both of them. And this is also a property that completely breaks down if you move to higher dimensions. So there's nothing like that in the literature. And also for later reference, the value risk is nothing but a quantile. So you all know this. Here's a picture. This is a set of lower quantiles. This is a set of upper quantiles. The intersection is a set of p quantiles of x. Usually it's 1 point for continuous distributions, but it could be also a true interval. Okay, here is the outline for the rest of the talk. I'm going to define lower C distribution functions, lower and upper C quantiles, the set value at risk, and then I make a few remarks about the market case. So what is the lower C distribution function? Before, I will fix some notation. So I start with a closed convex cone in RD, and its positive dual is a collection of all vectors which have a non-negative scalar product with the elements of the cone. So the positive dual. And a closed homogeneous half space is just everything that has a non-negative scalar product with a fixed vector W, the normal of the half space. And the bipolar theorem says that any closed convex cone can be represented as intersection of closed half spaces where the normals come from the dual cone. Okay, having this, we define the so-called W distribution function of X as the composition of the normal CDF, univariate CDF, of the variable W transpose X and W. And that means we consider the univariate CDF at the value W transpose Z. And you can write it as this, okay? And the lower C distribution function is just the infimum over the W distribution functions, where the W comes from the dual cone. You can exclude 0, that doesn't contribute much. It doesn't harm the definition if you include 0, but it's not really necessary. So it turns out that this is basically a new object. There are not many papers who deal with this type of function. And it turns out that, for example, this function is different from the joint distribution function, even if you take C as the RD plus. So we have greater equal in this relationship, and the inequality is strict, even if this cone C is RD plus, so the joint distribution function case. And you can already see this if you take a bivariate normal distribution and 0 for Z. So that is very easy to see. On the other hand, this lower C distribution function shares many properties with the usual CDF, the univariate CDF. For example, we have so-called affine invariance, we have monotonicity in Z, we have monotonicity in X, and we have some kind of right continuity. There's some, let's say, more technical condition, but it basically works if you replace the order in the real numbers by the order generated by C. So, and then we have some kind of behavior at infinity, which looks a little strange. And it looks a little strange because this expression here is not 1 in general. In most cases it is 1, but sometimes it is even less than 1. This is a new feature of this lower distribution function. The same applies for minus infinity. It has something to do that the cone sometimes may contain straight lines. And if the cone contains straight lines, many things break down that work in the univariate case. So as a summary, lower C distribution functions almost behave like the univariate CDF. They are, however, different from the joint distribution function. And if you put D equal to 1 and choose RD plus as a cone C, you get back, of course, the univariate CDF. So it's some kind of generalization. Now, what is a quantile? The price we have to pay for introducing, let's say, quantiles for multivariate random variables in a canonical way is that those quantiles are not vectors, like Ilya also discusses in terms of risk measures, but they're going to be sets. So that means a quantile function is going to be a set-valued function. So that's why I define this symbol here, which is a power set of RD that includes, for example, the empty set. Sometimes you can have the empty set as value, okay? And again, it's a two-step definition. First, we fix a W here, and we say the W quantile, the lower W quantile of X, is this set here. So everything that produces a lower W distribution function with a value greater or equal than P. So it's very close to the univariate definition. And then if you replace the W distribution function by the lower C distribution function, you get the lower C quantile of the random variable X. Okay, what is straightforward is that you can represent the C quantile by the intersection over the W quantiles, and again, the W comes from the dual cone. And what is equally straightforward is that you can reconstruct the lower C distribution function from the quantile. So basically, the lower C distribution function and the set-valued quantile are inverses to each other. This is the formula that shows it. Okay? And again, the set-valued quantile function shares many, many properties with its univariate little sister. Okay? For example, we have something, that is, let's say, this is a feature that we need to establish. This feature tells you that if you add the cone C to the quantile set, then you stay in the quantile set. And moreover, the quantile set is convex and it is closed. And that has something to do with the fact that the C quantile set is the intersection of closed half spaces. So that's by this formula. And then we have the usual properties. You have the so-called additivity, or I don't like the word cache invariance in this case because there's nothing invariant here. So I call it a translativity property. So if you add a constant vector to B, then this constant appears outside the quantile. And you have some kind of transformation with respect to linear operators. So that basically tells you if you transform the data set by A and you transform the cone in, let's say, the transposed manner, then you get the transformed of the original quantile set. So the statisticians call this affine invariance, let's say. Okay, we have monotonicity with respect to the P, and we have monotonicity with respect to the X, and the interpretation of this monotonicity is exactly like Ilya already mentioned in his talk for risk measures. We will come back to this later. So on this condition A maps into a special type of structure. It is the collection of all closed convex subset of RD which are stable under the addition of the cone C. And we use this symbol here to denote this set. And it turns out that this collection of subset is a so-called complete lattice with respect to the order relation superset. Okay, so this is the order relation that you need to apply in this set. And what is a complete lattice? A complete lattice is an ordered set such that every subset of this ordered set has an infimum and a supremum. And this is very different to the picture I showed you, where even in RD, some sets do not have an infimum or do not have a supremum. So, for example, for non-lattice cones, that is very straightforward. Here, it is always the case, and very surprisingly, I don't need to put any assumptions to the cone C. So the cone C can have empty interior. It does not have to be pointed. That means it can contain straight line. In particular, the cone C can be a half space. No problem with that. And also, I don't need to assume further assumptions like non-empty interior or something like that. Not necessary. So the cone C here is quite arbitrary. And still, we have this very nice order structure. And this is everything I'm going to tell you about set optimization. So this is more in the background, but there is a huge, let's say, theory behind this one line. Okay, one link to what people previously did in statistics. So as I mentioned, they define substitutes for quantiles for multivariate random variables, and they're based on depth functions. The earliest depth function is due to Tukey, defined in the middle of the 70s, and this is the depth function of Tukey. And you see here, the infimum is taken over everything in RD but 0. This is a difference to the lower C distribution function. And the depth region, the Tukey depth region, is the upper level sets of Tukey's depth function at level P. And now you can observe that only P between 0 and 1/2 makes sense. So bigger values are not possible. And the observation here is that Tukey's depth function is a special case of the lower C distribution function if you take the cone C as just 0. Just 0. So this is a very borderline case. And now you can start thinking about, if the cone is just 0, what is the order relation that is induced by this cone? And the order relation, of course, is that two elements are comparable only if they coincide. Only if they coincide. So this is, let's say, a very poor order relation. Very little comparisons are possible. Okay? In this case, one looks for so-called deepest points of the data set. And it turned out that Tukey's depth function, you may correct me, is very useful for so-called symmetric distributions, like the multivariate Gaussian distribution. So that is very nice. So they have some kind of center, they have to have some kind of center symmetry. So then it works very well. In other cases, there are problems. Another observation is that you get back the univariate quantiles for D equal to 1 and C equals C plus is R plus. So in this case, we get the univariate quantiles. And another nice observation that follows from these two observations is that in the univariate case, the quantile sets and Tukey's depth terms regions are different. So Tukey's depth regions are not a generalization of the univariate quantiles. Okay, so we basically solve this problem by giving a joint generalization of both things. So in the same way, you can define upper quantiles. And I'm not going to go into the details of this. Let me just mention that the upper quantiles map into the opposite space of sets. So the upper quantiles are directed in the opposite direction compared to the lower quantiles. You will see a few pictures in a second. The surprising result is that you can represent upper quantiles by lower quantiles in our theory. So what you need to change is the direction of the cone C. So instead of C, you consider lower quantiles with respect to minus C, and you replace P by 1 minus P, and everything works. And there is no other concept known to me in the literature that has this kind of property. Okay, you should compare this to the scalar formula, which is this one. Okay, here also lower quantiles are sufficient. So summary, as I said, the lower C quantiles are kind of set-valued inverses to the lower C distribution function. We have most properties of the scalar quantile, and it is a joint generalization of Tukey's depth function and the univariate quantile. So, and now I think you are kind of curious. So how do those quantiles look like? Okay, this is a very simple case. It's a 4-point distribution, uniformly distributed over 4 points. And here are a few quantile sets. Okay, so the upper sets, the blue sets are the lower quantiles. This for P between 0 and 1/4. And the yellow sets are the upper quantiles. So here 2 more cases for P between 1/4 and 1/2 and P 1/2. Here you can see that they touch each other nicely. And on the other end, this is for P between 1/2 and 3/4, P 3/4, and finally for P between 3/4 and 1. Okay, you can see, keep this picture in mind, okay? I will go back, keep this picture in mind. That is the, let's say, reflection of this picture here, because of the formula with Q plus and Q minus, okay? Okay, so in general, and that might be a disappointment to you, in general, we do not have that the set of quantiles is the intersection of the set Q plus and Q minus. That might be a disappointment. So this is different from the scalar case, and this is also, there is a reason for this. So in general, this intersection is empty. For example, here, okay, is empty. There is nothing in this intersection. So this is different from, it's a new feature compared to the univariate case. So here is a more sophisticated example. We took a uniform distribution over those 2 squares. Okay, and then the quantile sets look like this. This example, by the way, is taken from the Belloni-Winkler paper 2011, Annals of Statistics. So we computed our quantiles, and they look very differently from the quantile that Belloni and Winkler came up with. In fact, the Belloni-Winkler quantiles are non-convex sets. Ours are always convex sets. And some are, let's say, of the structure point plus cone, but some others are clearly not of the structure point plus cone. Okay, here's a different example. The 2 squares are moved in a different position. So here you have a nice quantiles of the structure, not of the structure point plus cone. So let's compare the concepts with a few things that other people have done. And as I said, one may think that the joint distribution function also gives rise to some kind of quantiles. However, if you investigate this, then you will see that those quantiles are different from our quantiles. They're even non-convex in general, and they're also even different, that was our conjecture first, they're also different from the convex hull. Our quantiles are also different from the convex hull of the joint distribution quantiles. Here's the picture, okay? So the green set is a joint distribution quantile, and the green and the blue set is our quantile. And here we thought, okay, maybe it's a convex hull, but then it turned out, no, it's not, because the green set here is a joint distribution quantile, and the green and blue together, this is our quantile. And it's clearly not, it's bigger than the convex hull. It's bigger, okay? Yeah, next point, if you know quantiles, you can easily define the value at risk. And if you know quantiles, you can also easily define first order stochastic dominance. And in terms of first order stochastic dominance, let me mention that there's in this famous book by Muller and Stoyan, there are several definitions of first-order stochastic dominance for multivariate random variables. And there is some kind of ambiguity, because they always come up with two different definitions, and both of them are kind of generalizations of the univariate definition. And this is because they didn't have this very nice property that upper quantiles can be represented by lower quantiles. So we can do this. So that's why we have only one definition, only one stochastic dominance in this case. So how does it work? So the formula is very easy. So you define the value at risk as some kind of lower quantile, as in the univariate case. I mean, the definition looks basically like the same. Okay, and then you can compute this in this way. And this formula here has a very nice financial interpretation. Because this x here could be some random future financial position. This little z here could be a deposit that has to be given at initial time in order to compensate for the risk of this position. And then this condition here, x plus z belongs to minus interior of h plus, is this condition here. And this means that if w would be the price vector, you're bankrupt. The value of your portfolio plus deposit is less than 0. So that means the value at risk includes all these, such that the probability for bankruptcy is less or equal alpha. And you control the alpha in the usual way, like 5%, 1%, or something like that. So, and that no matter what the price vector is. The price vector comes from some dual cone, which could be some market model. Of course, now you will say, that's not a market model because it's constant and you need to have random, and so on. Yes, I will deal with this a little later. Okay. So the function, the value of this function maps into this complete lattice. It is positively homogeneous, and at 0 it produces just a cone C. Okay, and it has this transitivity property here, as in the scalar case, in the univariate case, and it is monotone non-increasing with respect to the pointwise order. The same interpretation as Ilya gave for set-varied risk measures here. Okay, so the set-varied value at risk has all the properties that we know very well from the scalar, from the univariate value at risk, including the defects. It's not convex. It's not convex. Okay, including this. Okay, anyway, this qualifies the set-varied var as a set-varied risk measures according to some earlier definitions. So here is a picture. We took 50 data points. They represent some index values. And we computed the value at risk for this data set. And the feature here is you basically look into the value at risk. Okay, so it comes out. And the feature here is that it has this kind of boundary. So it's not of the type point plus cone. It is a polyhedral convex set with some, let's say, facet. Okay. So there are some scalarization formulas. So you can indeed represent the set-varied value at risk by scalar set-varied value at risks. Okay, but you need lots of them. You need all where the W here runs through the dual cone. Okay, so this can be done, and you can use this formula in order to compare the set-varied value at risk with other things. For example, it turns out that even if in case that the cone is just a RD plus, our set-varied at risk is a little more conservative than the component-wise value at risk. The component-wise. That would be, let's say, the starting point for Ilya to define some kind of risk measure. Okay. On the other hand, Embrechts and Puccetti define some kind of value at risk for multivariate positions based on the joint distribution functions. That was this kind of set here. And if you drop the boundary, so this symbol stands for the boundary, and C is RD plus, so then you get that our value at risk is less conservative than the Embrechts and Puccetti value at risk. And that has something to do with the fact that this set here is in general non-convex. So that was this example. And what we do, we construct a bigger set, which is convex, and could be even bigger than the convex hull of the Embrechts and Puccetti value at risk. Okay.
2 minutes.
Yes, 2 minutes. I know. So here is the definition for first-order stochastic dominance. In the usual way, let's say, I refer to the book by Hans Vollmer, Alexander Schied. Okay, I followed this basically in this respect. And you can represent the first-order stochastic dominance either by C distribution functions, or by our set-value quantile, or by our value at risk. So it's the same theorem as in the univariate case. Okay. And the last minute I will spend on market models. For statisticians, everything here is basically new. I mean, for financial mathematicians, maybe things are a little different because you are expecting some kind of market model and what's going on with the risk of some things that you can trade. Okay, so now we are trying to do, and this is basically work in progress with some other people, to incorporate the market model. And there are several ways to do it, and we decided to start from scratch. The obvious idea is make the quant C random, and the motivation from finance is of course canonical market models. Motivations from statistics, I don't know. I'm going to talk to many statisticians in the near future, and I'm not sure if it makes sense to analyze data with a random cone, okay? Because the cone changes with the data point. I'm not sure if I can sell this idea to statisticians. Let's see. Okay, so here is a random cone. It generates a random order. Here are potential quantiles, and this is another nice feature. The quantile does not have to have the same dimension as the random variable. Okay, you can ask me why, I can give you an explanation. Then there's a linear operator who maps the potential quantiles into random variables. That could be just an embedding. However, here's a nice example. You take m linearly independent elements of L0, and T is just a linear combination of these elements. And that means this T here represents something like the eligible assets, which can be used as deposits. And any linear combination of those Z's can be used as deposits. Okay, then you have pointwise cones. This is C of omega. This is a pointwise dual cone, which has this formula. And this can be seen as a one-period market model with M eligible assets. Okay, here is the CDF, no, the Y distribution function, because now we need to fix a Y and L0D. And then the C distribution function, where you take the infimum over the Y's in the pointwise dual cone. Okay, so that is the construction. The corresponding quantiles, same definitions as before. And now the feature is that many properties from the constant cone case carry over, but not all of them. And that's precisely the interesting point. Which of those properties do not carry over, and by what do we have to replace them? Okay, here is the var. That is basically the very same formula. And now you can define stochastic dominance. You can define the A var starting with the var. You can think about Kusoka representations. And of course, you can do data analysis and so on. So for me, and that is my very, very personal opinion, okay? Don't kill me for this. For me, this is something like a textbook way to introduce quantiles for multivariate positions. Okay, this is my textbook answer. The textbook is still to be written, okay? Okay, the test question for you is, where's the infimum in this formula? In the univariate case, you remember there's an infimum. So where's the infimum here? This is the reference, and thank you for following me into the depths of statistics. And my last slide is this one, and I have to make a reference to Yuri again, because this is our first conference to be organized in February next year. The first conference was 2012 in Wittenberg, and Yuri was a keynote speaker. Thank you, Yuri, for this, and thank you for inviting me here. It was my pleasure to give this talk.
So we have time for some questions.
I used to ask questions.
There is possible extension of this theory on more general order. So you want to have affinity, affine property, but this is because you consider an order generated by a cum. But one can consider, say, multi-utility representation of the order and so go further. Is it possible? Or it is not maybe so interesting?
This is a very good question. That is a question I think about when I can't sleep at night. Okay, so questions like this. And for example, the Belloni-Winkler paper that I mentioned, they deal with very general order relations. So they do not assume the vector order structure, for example. And the fact is, yes, and basically we are on the verge of, let's say, getting in this direction. And what is the problem? The problem is the complete lattice. So here the complete lattice is made of closed convex sets stable under the addition of the cone. So if you have a more general order relation, you need to move to another complete lattice. You cannot stick to this one. And the first answer to your question is yes, it is possible to construct a complete lattice on the power set of any ordered set, on any ordered set, okay? And the second answer to your question is, because the approach here was basically, I start with some scalar construction, like the lower W distribution function. So what is a corresponding construction if you don't have a vector order? You don't have the bipolar theorem. And for example, if you have a family of utility functions representing the order, so then yes, we can construct a complete lattice starting from this representation that looks very different and that could have very weird, let's say, properties. But it is very interesting from a mathematical point of view because you get lots of structure, lots of interesting mathematical questions. And I mean, I called quite a few times already the problem of maximizing multi-utility representation, I call it the 21st century mathematical problem. So this is, I think that the problem is difficult and it's totally open. I have some ideas, but I think much development is required in order to solve this problem. Yeah.
This means that we have a multi-utility representation with linear functions.
Yeah. One example for this is also stochastic dominance for univariate positions, because you can represent stochastic dominance of first order by all monotone utility functions, for example, okay, and integrals. So that means you have an order relation which is generated by a family of scalar functions. So how do you deal with this? And you know that maximization or minimization with respect to stochastic dominance is difficult. That's a difficult problem. So even more so if you move to the multivariate case. But it's very interesting, and anybody who wants to join this, very welcome, very welcome.
Okay, one last question.
So just a comment maybe. So for me, I would rather get rid of the order completely, because it's much better to talk about probability measures than work with cumulative distribution functions. So what you deal with is basically the smallest probability content of some family of half spaces, right? So the order is absolutely not relevant, and so this leads to Tukey depth if you take all half spaces. Yes. Now you take some half spaces, yes. And well, so this leads also to some kind of another depth function. But in statistics, the reason for use of depth functions is to detect outliers.
Yeah.
And there's a paradigm that the convolution of distribution reduces the family of outliers.
Yes.
This is like in finance, the diversification decreases the risk. Yeah. But actually, the action of this rule, convolution reduces outliers, exactly opposite to one which is common in finance. So, which means most of depth trim regions on high dimensions cannot serve. They actually satisfy exactly the opposite relation than the risk mirrors should satisfy.
Yeah.
So which means it's somehow the fact that Tukey depth obviously is not subadditive in the usual sense, right?
I'm not sure if I understand the last point.
But it's not coherent. It doesn't satisfy coherency property.
Yeah,
it's not
sure.
Coherent risk measure.
Yeah, sure. Yeah, it's more like a varied risk type of risk measure. Yeah, okay. Sure. Yeah. But the only point I don't really agree with is that the order doesn't matter. I mean, as far as I realized over the last few years, in many, let's say, practical examples, when you analyze statistical data, the order is present. The order is present. It's just not dealt with accordingly, let's say. So there is something missing. And we have one example, for example, if you take a medical treatment, so you have some kind of drug, you have effects and side effects. And of course, more effect is better, more side effect is worse. So then you have lots of data points that are your patients who take this drug, okay? So then usually the statistical analysis only refers to the data points, but not to the order which is present, because you know that more effect is better and less side effect is also better. So there is some kind of order, it's naturally given. So that means all the data analysis should refer to this order. And there are many other examples, I mean, of this type. Okay, so that's why I think it is much better to explicitly deal with the order because it's present anyway. Preferences in economics, cons in finance, and so on and so on. So and that's why I like this. It's my personal preference, okay?
Okay, thank you again for those
There was
nice...
one question over there.
Do I understand right that this approach is completely different from another possible approach to find quantile functions? We take, say, uniform distribution on, say, unit cube, and then by Macken's theorem there exists a convex function. We look up to a completely fixed such that its subgradient corresponds to the quantile function in the univariate case.
Yeah.
It is completely different.
It is completely different. I discussed this point with Mark Helen, and because they use Monge, Kantorovich, mass transposition, let's say, approach to quantiles. And we had a long discussion, and after the discussion, we agreed upon we have to merge the two approaches.
I also discussed this.
Yeah. Yeah. Okay.
Okay, thank you again for those nice talks, and thank you again to the speakers. So.